There's no connection. There will be no link between the different nodes. Once you invert, oops, I meant to write it like this. Once you invert a matrix like that, typically sparsity is all lost. So the inverse of a sparse matrix typically is not sparse, except for things like the identity or stuff like that. That's sort of an unusual case. Typically, not always, but typically this will be a full matrix. And so what that says is that the time derivative of omega depends on all the power angles. So we've coupled our systems together. Right? And we sort of knew that before because we knew that power flow would couple them all together. But now we see explicitly how the dynamics are coupled, how the dynamics of a single generator depend on the power angles of all the other generators. That's what's captured through this equation here. So now the question is, well, they're all coupled. We know that. But what if we do just still run PID control, right? So what if we still just pick U to be equal to negative Kp times theta minus theta d, I guess because I in all of them, minus K d omega minus omega I, and I guess their omega d is always the reference omega. So we can apply this, right? What happens if we do? This is sort of the wrong thing to do, as I was saying before, right? Because we know from our system here the dynamics are all coupled. We know that how I'm going to evolve really depends on what everyone else is doing too, not just me. Yet this is controlling the system based only upon looking at my node. And so does this actually work? And kind of the surprising thing is that it isn't the fact that this, well, I guess the surprising thing is just how often this does work okay. Because it really shouldn't work that well when you think about it. But it does work in a lot of cases. And what this says is that effectively, the effect of other generators, there is an effect, obviously. But we can kind of treat that like noise almost. We can kind of treat what everyone else is doing kind of as noise and just try to control ourselves, ignoring what everyone else is doing. And that actually kind of works. So that's actually a very sort of impressive thing. And it's also why, by the way, PID control is just so widely used, is that even when systems are coupled, it still can actually provably work and give you the right solution. And it's much simpler to implement sometimes than, imagine if these are real generators, for example, to implement a control that would depend on everyone else's power angle, you'd have to know, you have to have some way of communicating with other people and knowing what their frequencies are and what their actual power angles are. That would be pretty tough. Just knowing your own is a lot easier. So might think this would be a lot easier to implement, and if it does work, then we might want to just use that. So here is some plots of PID control. So this is a controller that has both, and I guess this is actually also plus or minus Ki times. I'll write it as a sum, though. A continuous time, it would be better done as an integral to time t of theta I tau minus theta I d. Something like that. And you might have a delta t in there, something like that, depending on how you write things. But this is a plot of just doing that. And the impressive thing, as I said before, is that even though these are 5 generators, they're all coupled, it gets all of them to their desired power angle and to their desired reference velocity, which is the same for all of them. They'll have different desired angles, but with the same velocity. As I said before also, it's probably more common to see power control done without this term, because knowing your absolute true power angle is a little tricky. You have to have some sort of synchronized clock amongst all the different generators. That isn't actually that common to have in generators. So frequently you'll actually just control based on frequency. And you let your power angle kind of be whatever it has to be. Or there is some ways of controlling that, but that typically is done in a slightly different way than just this. But here, for simplification, we'll just sort of say that we know our power angle, and we're going to control it to some reference point that depends, of course, on your desired position depends on how much power you want to generate and all that kind of stuff. It'll affect how much power you generate and that kind of stuff through power flow, of course. Okay, so having said that, PID control works great, but PID control is kind of an art in a lot of ways, right? Because you still have to tune all these gains here. You have to choose what these things are. And while there is plenty of ways to go about doing that, and there's a huge amount of literature on how you best pick gains, all this kind of stuff, for a lot of real-world systems, it's kind of still a matter of trial and error. Maybe they don't really try it out on real systems. I'll try it out in simulation first, or things like that. But there's a lot of kind of fine, and then they'll tune it on the real system. But there's a lot of kind of guesswork, because if the real system is not quite as you think it is, for example, then you have to kind of fiddle with these parameters, see how they do. Even if you do know the system, it can still be really hard to sort of know exactly what those gains should be. And this is without going through any sort of math, just by sort of thinking about, well, what should my numbers here be? It can kind of be hard to pick what these are, right? And what typically is common is that people sort of have an intuition about what these things do. So essentially, the P gain will get you to your desired position faster. The D gain will kind of add a drag to your term, because it'll also try to match your desired velocity, so it'll slow down the system from oscillating too much, like we saw in that very first graph. So there's some notion about what these things do intuitively, and then the I gain corrects for steady state errors. But these things are very interrelated, right? For example, a common effect in PID control is something called integrator windup. This is the case that at the very beginning, systems are just kind of doing something. It's unclear what they're doing. They're sort of executing stuff initially to kind of get close to the optimum. But in order to get there, they could do things that actually have pretty high error. So like in some initial situations, this term here could be pretty high. That term is still going to be added to, and it's going to go down. You're going to control the system. It's just that you haven't quite gotten there yet. Even if you ignored this term, you would still be doing better than you are at the very beginning. But this term then gets added to the integrator. And so if you have this gain too high, you'll put a really high weight on these things that build up over time. And what happens is that you kind of, have the same effect with PD control, essentially, or just the P control that we saw, right? Where you kind of overcorrect and undercorrect and overcorrect. And it just becomes very hard to tune these things sometimes. Now, that's not fixed by techniques like LQR, but techniques like LQR, going back to this optimal control setting, they oftentimes can be a little bit more intuitive about how we do these things. Because remember, we'll return to our optimal control formulation here, where where our goal now was not just pick some numbers and see what it does, but we actually instead defined the cost function, saying our cost was defined as some function of the state and the control. Maybe it's some deviation between the state and the control from their desired values. And often it is a lot easier to pick those costs. It's just very intuitive, right? Cost is just how much do you care about this term versus this term. Those can be a lot easier to pick than gains. And from a high level, what LQR does is it takes a cost function specified as costs on the state and the controls, and it will produce a feedback controller for you. The optimal feedback controller, in fact. So that's the high level. Now I'll sort of delve into the details of what it does. We won't get too involved with LQR here, because the actual derivation is a little bit tricky. I can point anyone to that if they are curious about it. I'm just going to tell you the result. I'm not going to show you how to prove this, but it's good to know the result. And actually, the result by itself is pretty useful on its own right. And because MATLAB has commands for all these things, you can easily type them in and get the solution to them. So, as I was saying, to start off motivating LQR, remember that we are returning that to our optimal control framework. And so what I mean by that is I want to pick controls that minimize this cost to go, which is the sum from I equals 1 to some horizon t of, sorry, I shouldn't call this cost to go. I should call this just a general cost function. But it's a sum of cost functions every time. Cost to go has a particular term in in some LQR stuff. It is also cost to go, but don't worry about that term. It's just the sum of the costs. And we want to pick our controls to minimize this whole sum of costs. So what we remember from our first set of slides on this, and this is how I kind of introduced optimal control on the very first set of slides, essentially optimization problems that will pick controls to minimize some objective, some cost. Now, remember that I said, in general, this is very hard to do. But for the case of linear systems, there's sort of the one case where we actually can do things well, right? Because if we have a system like this, xt plus 1 equals axt plus b ut, this equation here is linear in the states and in the controls. And so we can put this into an optimization solver, and this actually is a convex constraint, right? So we can solve optimization problems with this constraint. The other thing I said you need, right, is you need a convex cost function. You have to make sure this is a convex function here, otherwise it's hard to minimize. It's going to be hard to minimize. And so an example of kind of a canonical convex function is quadratic functions. So if our dynamics are given by this, and our cost function xt ut is given in terms of quadratic costs, in this case I'm just writing it in terms of L2 norms, so that's saying this is equal to some matrix Q times xt, 2 norms squared, plus some matrix R times ut, 2 norms squared. If our cost is this, then it turns out we actually can solve that optimal control problem I was telling you about in the very beginning, minimize some of the costs subject to these dynamics, very efficiently. And this is exactly what the LQR algorithm does. It solves this optimization problem. Minimize this subject where C is defined like this, subject to this constraint. It's important to note that the name regulator here comes from the fact that in this system, notice our cost is always penalizing big states and big controls. So 0 state and 0 control here is the best state and the best control. And from our dynamics, we know that if we ever get to the state 0, we can keep applying 0 control and we'll stay in the state 0. This is different from, say, an affine system where we would have this extra term here. We're not thinking about that. We're just thinking about a linear system. Now, LQR can be extended to all these cases. It's not hard to extend to an affine system or cases where your cost is something like this, q x t minus x star or something like that, where you want to get it to a certain point. And in fact, I'll show in a second how we can easily apply this method to controlling a system like this. But just for now, for the math, I'll think about this being the system and this being the cost. But it will be easily applicable to this case in a second. OK, so here's our state, here's our cost. And kind of the amazing thing about LQR is, so first of all, we can write this as an optimization problem, right? We just want to minimize over the states and the controls, where we're really not minimizing over the states. That's sort of actually given as fixed. We also probably would want to say here that the initial state would have to be something. So that would be one more constraint we would add here, but actually ends up not being that big a deal because what you do doesn't depend on the initial state, kind of also surprisingly. Or rather, the solution given by LQR is in a way independent of the initial state, which is sort of really surprising. So we can solve this problem here. And let me just, I'll write this down, because I should add that left out bit here. But we want to minimize over xt, or x1 to t, and u1 to t, the sum I equals 1 to t, q, or maybe I use t there, q xt plus r ut, convex cost, so everything looks good. Linear constraints, we can still handle those. And I'll even add something like x1 equals x1, 0. So that's given to us. This is convex, so we could just plug it into a quadratic programming solver. And in fact, it's a quadratic program because the objective is quadratic and all the constraints are linear. So you can write it in standard form and solve this as a QP or solve it with YAML. But it turns out we can actually solve it even more efficiently than that. And this is with this algorithm called LQR. So I won't go into it, but actually on the homework, what you'll see is you actually can write this whole thing as a big least squares problem. And so what LQR does essentially is it efficiently solves this big least squares problem, but does it using a technique called dynamic programming that kind of keeps track of things you've computed already to compute things that you're going to compute next. That's all it's doing. It's just solving this problem in kind of an efficient way. I should say that's what the discrete time or finite time horizon LQR is doing. We'll get to a second in what was really cool about LQR, which is that it also works for infinite horizon problems. But ignore that for at least this slide. OK, so we can solve this problem. And what's really neat here is that the optimal solution, so the best UT, the best control you could possibly execute at the tth time, is actually given by a linear feedback policy. So it's actually given by some matrix KT times the state at that time, where this KT comes out of the solution of the LQR problem itself. So if you just solve this as a quadratic program, you wouldn't get this form. You would just get a solution for xt and ut. But what's very cool here is this is actually given to you by a linear function. So whatever your sort of xt's that come out are, this relationship will hold here for some kt. And in fact, you can easily solve what these kt's are to just compute what those things should be. And so then if you know x1, you can compute what u1 should be, then you compute the next state. You can get the whole sequence of states here. But really, this is actually even more general. Because what's nice about this is it actually does not even depend on what your initial state was. This holds true here, independent of the initial state. So you get the same with the same case. So you get the same feedback policy regardless of what your initial state is. And you can easily compute those just in this dynamic programming fashion. Just a show of hands. Has anyone here seen LQR before or looked at it? OK. So then you probably know how to compute those things. But for everyone else, you'll have to just trust that MATLAB will do it for you. The very nice thing here is that this gives you not just a sequence of states and controls, but actually gives you a feedback policy, right? This looks, and we'll do this more in a second, but this looks just like kind of a PID controller. You take your state, which includes maybe derivative and actual angle terms, in our case of generator, multiply it by some matrix here, and you get your controls out. They, in fact, are very related, but it's sort of nice that instead of just getting a set of controls, set of states, you actually get essentially a controller. And what this lets you do is you actually can plug this into situations there where maybe your state doesn't quite follow what you expect it to do, but it will still work pretty well in practice.
Quick question.
Yeah.
So how is the U star T different than what we're getting out of the quadratic program? Because we're minimizing over the state.
Yeah, exactly. Right. So if you solve this problem just as an optimization problem, to solve it as an optimization problem, you have to also give it an initial state. So you would say x1 equals some x10, right? What you will get out of this solution exactly satisfies this equation. You won't actually get the k's out of this, right? Because that doesn't come out naturally. What you would get is you would get a set of states instead of controls. And then it turns out that if you take your, if you solve it the other way, the LQR way, and get these k's out, and you take u1 equals kt x10, that would give you the first u star you get out of here. If you then apply it to the linear dynamics, you would compute x2, and that would be the x2 you get out of here. So the solution you get out of the LQR problem is exactly what happens if you take these controllers and plug in the sequence, the actual state that you started on. That's going to give you the exact same solution as if you just solve it as a quadratic program. What's nice about LQR is it actually returns these actual feedback matrices, so you can apply it really to any initial state you want without having to resolve the system.
So there would be only one matrix K.
So here, no. So here there are several matrices K. We'll talk in a second about what happens when you only have one. But here, we are actually optimizing over a finite time horizon. So I'm optimizing from t equals 1 to t. And in this case, the k's, in theory, are all different. what will actually happen is that several of the first will be essentially identical, and the last few will be a little different. And what this corresponds to is, remember, our intuition of control was that if you sort of think long enough ahead, you'll take actions that sort of steer the state toward a good location for the future. Whereas if you just look at the next step and that cost function, I would always take the control action 0. Because the control action 0 will have no cost. I have to already suffer whatever cost I'm in to begin with. And I'm not even thinking about one step ahead. I'm just thinking of my current time. So I'll always just pick control 0. So something like this happens in LQR, where essentially you care about the controls, bigger controls, at the very end of your sequence of states. So when you get close to t, you want to make sure your control inputs are small. But at the beginning, you sort of care more about guiding your state to the right location in space, because that'll give you more cost later on. And so what that corresponds to in these solutions, actually, is that k at the very end is going to be different from k at the beginning. What happens in practice is that you actually get a whole sequence of these, and only the last few are different, and then quickly they converge to a steady state solution for the case. And actually, we'll see what that is right now. Because, yes, it's true. If you ever run LQR, and if you run LQR in MATLAB, in fact, it'll give you 1 k. It won't give you a lot of k's. So what does that actually correspond to? What that corresponds to, actually, is an infinite horizon problem. So let's now replace this thing with the sum from t equals 1 to infinity. Now this is going to be hard to solve as a quadratic program, right? Because there's an infinite number of variables. We still don't know how to do that. And it seems a lot harder now. But there are two very cool things that happen here. The first is that this cost, even though it's an infinite sum, is still finite. Okay, so it's still less than infinity. And the reason for that is, if this system is controllable, then we know we can guide the system from any state to any other state within some finite amount of time, right? That's what we sort of talked about with controllability. So if the system is controllable, and that's actually, it has to be controllable. If it's not controllable, this will be infinite. But if it's controllable, then we know that we can guide the system to the 0 state in some finite number of steps. So that'll have some cost. And then once we actually get there, we'll never incur any more costs, right? Because we'll stay in the 0 state by applying 0 control. And that 0 state, 0 control, has 0 costs associated with it. So we know that this optimum is less than infinity, because we can just know by controllability that there exists some sequence of states and controls that has a cost less than an infinite cost. So the best one is actually going to be less than that, right? The best one will be even less than that. And what it really is that this typically is an exponentially decreasing function, so it's never actually 0, but it sums to something that's finite. Is what you actually get here. So that's the first cool thing, is that even though this cost looks like it could be infinite, it actually is not. It's finite. The second thing that happens is that the solution here is actually given by this, a fixed k, such that for all time, the optimal action you take, so if you could solve this for an infinite amount of time, what you would get is you would actually get that there is a single k matrix such that you can compute all the optimal states and all the optimal controls by just plugging them into this equation here. For some k, you multiply k by xt and you get your best possible control. That thing here will achieve the best possible cost here. And again, the derivation is a little bit involved. It essentially involves looking at that last equation, the solution, the recursive solution that we had for the finite horizon case, and showing that k matrix, or rather the cost, will actually converge to a steady state cost that satisfies some equation, and you compute this k based upon that equation. That's a little bit, I'm very hand-wavy there, but that's sort of the basic idea. But what you need to know is that this form gives a solution to this problem. And in fact, it doesn't even really depend on the initial state either. It's just for any, because you just plug it into that equation. So for any system like this, the optimal solution will be of that form. And the way you get it in MATLAB, I'll just say, is you say k equals dlqr, pass a and b as the first two things. Q transpose times Q and R transpose times R is the next ones. That's for the cost being in this form. Oftentimes, you'll actually see costs written in this form, something like xt transpose q xt. And in that case, this q is really that q transpose times that q. I'll write it like this, right? So we know that this q xt 2 norm squared, that equals xt transpose q transpose q xt, which equals xt transpose q tilde xt. So we'll actually usually see the LQR costs in this form, but the quadratics are a little bit more common for what we are, and especially also when you have things like deviation from states, it's a little more natural to have them as quadratic functions. So I write it like this, but you might see this too. And actually, the parameters that you pass in are really this q tilde matrix. So in our case, we pass in q transpose q. The D here, by the way, stands for the discrete time version. If you have the exact same thing, but you want to minimize this in continuous time, this is actually even cooler that we can solve this because it seems even harder to solve. It's now a continuous time system. If you want to minimize over x, u, and I won't write besides because these are actually infinite dimensional continuous functions, the integral from 0 to infinity of this thing, qxt, I'll write this like this actually, qxt plus rut dt. So we're now our function is an integral. Our objective is an integral because we're in continuous time, subject to x dot t equals a xt plus b ut. It's the exact same call. Again, you actually have the fact that ut star equals some matrix k times xt, and you actually will use this in the homework. For the more advanced problems, actually do some of this continuous time stuff. It's described there a little bit more too, but so don't worry too much about it. But you can solve this problem, and the solution is of this form. Again, a single k matrix where it's actually the exact same thing here. You just leave off the d. So LQR typically refers to the continuous time version in MATLAB, and the DLQR refers to this discrete time version. So this is actually sort of an amazing thing that we can really solve these things. We have an infinite time, continuous time, infinite horizon cost function, yet we actually can get the optimal solution. And this computes it pretty quickly also. It doesn't take very long to compute that. Much faster than writing an infinite size optimization problem, maybe like discretizing after some amount or something like that. Okay, so that's LQR. And let's now do the example of applying LQR to our generator task. And this is going to be a little bit trickier because unlike the systems I showed before, our generator task is not quite exactly linear, right? It actually is an affine system because we have this extra term that depends on the load. That's the sort of thing when you add the load, and also, depending on how you write it, it can also depend on the reference velocity. So, yeah.
What are the general applications that PID and LQR are used?
Oh, they're used everywhere.
And which one is better?
So which one's better? So at the end of this, I have a slide on some of the pros and cons of PID and LQR control. I think from what I've said so far, the takeaway is that PID is simple to implement, does not require that you know a model of the system. I mean, LQR, to call this function, you have to pass in A and B. So you have to know what A and B are. If you're a little bit wrong, it can still work sometimes, but that's sort of the same thing with PID control. It sort of works even though it shouldn't work. PID control is simple to implement, but it can take a lot of tuning, especially with the integrator stuff. It really can get kind of nasty. You actually can implement integrators in LQR too, which you will also do on the homework. But it's actually no. You won't use it with LQR. Just implement an integrator in continuous time, but not with LQR. But you can implement integrators with LQR too. LQR maybe I'll actually hold off on that comparison for a little bit, because I think I will touch on some of those points. So we'll hold off on that. But I'm not going to go through this in details, but essentially what it is, what I'm showing here is just the dynamics of the generator, the multi-generator system, written in linear form. So this is written as, can be written as a system, x dot equals ax plus bu plus a, right, where x is just going to be the vector of thetas and vector of omegas, and then these are a, b, and u. Or sorry, a, b, and little a. OK, so that's just really rewriting stuff that I've already written before, so I won't go through this. But now the question is, how do I apply LQR to this? Because it's a little different here, right? It has this thing. And our costs are a little bit different, too, because in LQR, you always regularize away from 0, right? But we know from power systems that you're not ever going to have all the generators having 0 power angle, and then satisfying all the power. Because if they have 0 power angle, then there wouldn't be power flowing between them, at least. I guess they could still flow to the loads. But in our case, you're not going to be able to attain 0 power angle for all generators and still satisfy all the loads in the case that we're looking at here. So you need to actually attain a different power angle, different generators. And the one you want to attain, you can determine that through power flow, right? So you solve power flow, give it some powers, and then it'll tell you what the angles have to be. So our cost function we actually care about is something that looks more like this. First of all, we have, theta minus theta star would be our cost, and then also say omega minus omega ref. So in both cases, we actually have a cost function that's the difference between where we are and where we want to be. And we have this extra affine term in our dynamics, so it's maybe less clear how to apply LQR to this case. All I want to show here is that actually there's no difficulty at all. You can still apply LQR to this case exactly. And here's how you do it. First of all, I'm going to look, I guess I don't really need to do this, but I'm going to think about the discrete time case. So I'm going to say my system is xt plus 1 equals I plus delta t, original a, xt plus delta t, b, x, b, ut plus a. OK, just to, I guess, delta ta. And this is, I'm just going to define this as being a tilde, so it's a tilde xt plus b tilde ut plus a tilde. OK, so now we still have an affine system here. And what we're going to do now is I'm going to say, let's look at the system around an equilibrium point. OK, and what an equilibrium point is, this is a control and state that when you plug in that control and state, you get out the same thing. So I'm going to look at an equilibrium point, which is a state and control such that x star, which is our state here, equals a x star plus b u star plus a. All right, and this essentially, what this is an analog of the 0 state for affine systems. So remember, for a purely linear system, if we start at state 0 and plug in 0 control, we always stay in state 0. So it's kind of easy. 0 and 0 was always an equilibrium point for that dynamical system. In the case of an affine system, 0 will no longer be an equilibrium point because we would add a to it. So xt plus 1 will be equal to a if xt is equal to a. What we do instead is that there do exist points like this, where the state that we get out is equal to this plus some fixed control plus a. In the case of power flow, what this would be is x star would actually have the desired angles in them. X star would be the sort of the desired power angles, and everything being the reference velocity. B would be the powers that you need to produce to get those power angles, so the powers you get from power flow. And then A is just what we had before. And so actually, if you take the power flow equations and plug them into this, basically x star here would equal theta desired and omega ref. Right? And if this, and then u star equals pg, but this is the pg that you get from the power flow equations themselves, right? Where essentially p equals b theta. So for some theta that satisfies these things, I guess I'll write it like that. If PG is the component here, then the loads are known and everything like that, then this would be how you get x star and u star. OK, so now I'm going to do the following. I'm going to write a new linear system. Sorry, I probably shouldn't have erased that yet, but you have to figure out some of that for the homework anyway, so you can get it on the video too. Freeze the frame really quickly. So now I'm going to write a new system that is based on these two properties, but which is a purely linear system. OK? And this is very simple to do. I'm just going to take this equation here, xt plus 1 equals this thing, approximately equals that. And I'm going to subtract x star from both sides. So this will imply xt plus 1 minus x star equals a tilde xt plus b tilde ut plus a tilde minus x star. All right. I'm going to plug in a definition for x star there. So this equals a tilde xt plus b tilde ut plus a tilde minus a tilde x star minus b tilde u star minus a tilde, which equals a tilde xt minus x star plus b tilde ut minus u star. OK? So I've just subtracted the things from both sides, subtracted x star from both sides, and plugged in this that definition of the equilibrium point. And now, if we define a new system in terms of where the states are no longer the absolute state, but it's the actual delta from the desired state. So xt is really xt minus x star. Then that system in the deltas actually does correspond to a linear system. So there's no more affine term because those have all canceled. Right, so that's the basic idea. We use an equilibrium point to convert this affine system to a linear system in the difference states. And now we apply L-quadratic to this thing because our costs really are of the form something like ct ut equals q xt minus x star, which is exactly just our state. So this actually equals just a purely quadratic function in our delta states. And what we get out then is a controller that says delta ut star equals k times delta xt. Right? And this also would imply then that u star t equals u star, so our nominal control input from our equilibrium point, plus this matrix k xt minus x star. So look at this form here. What we see with that is that this looks a whole lot like PID control. Right? Maybe I'll erase everything. This is a big derivation. It's all on that slide before, so I'm just going to erase it. It's all on the slide before. I'll just write our last thing we got from that, which was to say that the control we execute equals some term u plus k times x t minus x star. All right, now if you remember from our PID discussion of PID control, this looks exactly like a PID controller, or just a PD controller with a feed-forward term. So what we do is, and in our case, this would actually be, this would be P, the generators. This would be K, but I'll write it like K theta and then K omega times this thing, which is really theta minus theta d, and then omega minus omega ref. So this looks just like PID control. We have our feed-forward term here, which is the same in PID control. And we have some matrix K theta, which is sort of actually Kp. I'll just call it K theta here, times theta minus theta d. The only difference between this and PID control was that for PID control, those terms here, this K and this K theta and K omega, were just diagonal matrices. We only looked at the control node I, generator I, we only looked at the difference at node I. What that corresponds to is both these things being some multiple of the identity. And if you use the same gains in all of them, this would just be, PID control would just be negative KPI times negative KPI, negative KDI times the state change. So from this high level now, what we see is that the optimal LQR controller for this system ends up having essentially the exact same form as the PID controller. It's just that because these things are full, it means that the controller, we do look at other states in the system in order to pick our own control. We actually look at what is not only our own difference between where we want to be and where we are at, but where's everyone else compared to where they want to be at. And we use all these things together to find the optimal control. Now, in terms of which one is better, there are some advantages and disadvantages to both. The nice thing about LQR is that it oftentimes is easier to specify costs than it is to specify gains. So it's hard for me to look at this system, say, and know what gains are right there. And if I see some behavior, I don't always even know how to change the gains to get better behavior. I mean, I can a little bit because you develop an intuition with these things, but it's really hard sometimes. It's much easier for me, and this is speaking kind of personally, maybe people that have worked in PID control for 20 years have a different opinion here, but for me it's a lot easier to specify costs on the state and on the control. What that means is if my state here if this state is just too far from where I want it to be, I'll just turn up the cost on that. I'll make the Q corresponding to that term bigger. And I typically pick Q here, by the way, to be some multiple of the identity, or at least a diagonal matrix. I almost never have cross terms in Q, even though you can. It's just usually the identity times some diagonal matrix that just weights these different things. So I'll just specify some weighting. If these are too far away, I'll turn up that way a little bit. If it's maybe moving too fast, oscillating too much, I'll turn up the cost on this. And if it's executing too big control impulse, I'll turn up the costs on the U's. Now, of course, I'm talking about tuning still, right? So you could just easily say, well, you could do the same thing with gains, right? You just tune up one gain, turn another gain. I will just say from personal opinion, I find this a lot easier to do than tuning gains, because gains affect all those things. They affect the cost of different things in very sort of subtle ways, and so it's much easier for me to do this. Now, K for LQR, it is important to note that these matrices will typically be full. So they do need to know what's going on at other locations to actually do something good at your own location even. There are variants of LQR that try to do similar things to that with diagonal matrices, but those are not exact anymore. Those are now going to be approximate methods. And so typically LQR will need to have this communication, say, to do it in the exact case. And that's true even when you have diagonal costs. You still will typically have dependencies between different states that are brought on by the dynamics themselves. So that's LQR. Now, and I should also say, if we sort of look at how it does, this is the sequence of derivation from the desired state and from the desired angular velocity here, and that's a pretty smooth type of control. That actually is controlling it very well. It's actually not, so let's scroll back a ways, it's not sort of too different from what you got with PD control. And of course, you can get these things to look good. when we also we know the feed-forward term here because we assume we have a model, so it looks better than the integral control, even when I've tuned it a little bit. But it's not like it's just blowing us out of the water either. The integral control looks pretty good too. So this might be a little bit better, but it A, knows the feed-forward term, and B, does something even better because it has all this communication between all the different nodes. But it is doing the optimal control, so at least according to this cost function, it definitely is better than PID control. It has to be. It's the optimal according to that cost function. So the time we have left, let me talk about an issue with LQR and then how we might solve that. And this will bring us sort of full circle back to control via optimization again. So LQR, the state sequences that we get and the controls we get, they all look beautiful, right? They're sort of very smooth. They have a feedback controller. Everything looks nice. If you ignore maybe the difficulty in communicating, say, everything looks nice. One downside to LQR, though, and this is actually the exact same thing with PID control. PID control does not fix this, is that at least in its naive form, it can often specify controls that are not very realistic, right? We're saying whatever the deviation is between our state and the desired state, just add that to your nominal control input, to your feed-forward control. So multiply it by some k and I'll do that. If k has very big entries, this term here can get very big. And what that means is you can get controls that are really far away from anything you actually ever do. For example, this is the power that all the generators need to apply to attain their power. And actually, don't worry about some of them being negative because some of them have a generator and a load on them. But some of them don't. Some of them actually are positive in steady state, and they initially say to go negative. So there's no load at that node. It just says your initial power has to be negative. Essentially, it's trying to slow them down so that other ones speed up ahead of them. Now, that's great, except for the fact that you probably can't suck off 2 megawatts of power just out of whim, right? If you're a generator, you can't just construct a fake load that does that. So maybe you have some wiggle room. Maybe there's some little bit of load at your node. So you can do some stuff, but you can't do sort of these arbitrary these arbitrary linear functions of important linear functions. This is a linear function here. You can't sort of execute however large controls that you want in order to achieve your desired behavior. And this is, you can certainly use heuristics, like just taking it and clipping it to the allowed values. That works fine in a lot of cases, but it's not optimal by any means. And PID control, PD and PID control have the same problem here. The real issue here is that LQR and PID control cannot inherently capture even convex constraints on the control inputs. They give a linear feedback policy which inherently is unbounded. Because if your state deviation gets unbounded, so will everything else. And because of this, actually I should say that there are some heuristics here. You could take, as I said, you could just take the controls and clip them. You could also tune your costs or your gains, right? So if your controls are just a little bit too big always, you just increase the penalty in LQR on those controls, or in PID control you just decrease the value of the gains themselves. That does work. Sometimes it will decrease the value. Then if you get an even bigger deviation, you'll just have the same control input. But at least for a fixed state deviation, you will execute a smaller control then, if you tune the cost or the gains. But for both those cases, it's really hard to guarantee how they're going to perform. It's really hard to say, I will never execute a control that's bigger than this amount. I should say that it's hard to say those kind of things while maintaining any statement about optimality. Because when you do things like clip controls to regions, you lose all guarantees about optimality. That just go out the window. This is no longer optimal for that LQR cost function if you also include constraints. And in fact, there's no linear feedback controller in that case. Even a clipped linear feedback controller is not the right thing to do. So what we can do instead is sort of return to this paradigm of controlled optimization. Suppose we have a finite horizon and we have our LQR costs. We start in some initial state. I'm putting that in explicitly now because when we have actually solve this as control, we need to put in that initial state. We can't just sort of make it up whatever it wants to be. We have to say what it actually is. We have our dynamics. We have a quadratic cost. It's still a QP. We can solve it. Everything's great. We also know that in a QP, we can also put inequality constraints in the variables, right? Linear inequalities. So we can just as easily add things like, well, the control has to be bounded within a certain amount. Or even things like the state has to be bounded. It's sort of like a hard cost function, effectively, right? It's saying that the state can never get above these things. That is essentially saying the cost there would be infinite if you ever do get outside that range. Okay, and while you can no longer get a linear feedback policy that will solve this problem, it is still just a quadratic program. So we can just plug it in to YALMIP or anything else, go ahead and solve it. And when we do that, we get things, oh, I should already say it. So this is an example of generator control with the nominal power limited to the range of plus or minus 0.5 PUs, whatever units they are. I forget what they are for this power system, but anyway. 0.5 PUs plus or minus the nominal control that we want to apply. And we just solve it with YALMIP. And it takes about 10 seconds for YALMIP to solve it with a time horizon of 10,000. So this is a pretty big problem now. It's a 10,000 step problem, and it takes about 10 seconds. The reason why it's so fast is that this problem has a lot of sparsity. So these things, although there are 2,000 variables, there's a lot of sparsity in those variables. They're ones are only related to the next one. They all have sort of this right sparsity pattern. So you can actually do quite well. And this is just essentially those A's and B's that I got from discretizing the generator equations before. Importantly now, the output for this is no longer a linear feedback controller. It is just a sequence of controls. And we'll get to that in a second. I'm going to go through, maybe I'll return to this a little bit next class, but I want to get through kind of to the punchline here. The output you get is just a sequence of controls, and that's going to come up again, especially when we talk about systems with noise in them. So here's what it looks like. So here, again, are the sequence of state deviations from the generators. After the time, it's able to get it to the desired location. It takes a little bit longer, but that sort of makes sense because we're clipping the allowable range of the controls themselves. And here is what the actual generator powers look like. So remember, go back a few slides. For LQR, we had these powers that were, really, really negative here. This was much lower than, it's essentially sucking up a lot. It's asking generators to sort of suck up power, or consume power rather than produce it. Whereas with the optimization problem, the allowable range of powers is always clipped between 0.5 below and 0.5 above whatever power we sort of want to nominally have for that generator. Okay, so but yet still we're able to converge to the desired location here. And this is actually a pretty complex control input though, right? I mean, it's sort of strange, right? Like we could go as negative as we can, then as positive as we can, and then we sort of do a little thing. I could not come up with an easy control law that would do that. It actually, if you just clip LQR controls, it doesn't look that different from that, but it does look different. And this is now the optimal set of controls, obeying those constraints to achieve what we want to achieve. So last slide here, and I'll go back to this a little bit, but I just want to finish up in the minute I have left. PID, easy to implement, does not really require a model system, but it requires a lot of gain tuning. You have to tune these gains, and that can be really hard. And it actually also say it does not always apply to multivariate systems. It can, but sometimes it just will not work at all. An example of that is oftentimes if you have fewer control inputs than you have systems, it can actually break down. And there's just there's no way to do this just by looking at individual systems. LQR, it gives a feedback controller. It's very nice because it gives a single feedback controller you can always apply. It's easy to compute with MATLAB. It does require that we have a model of the system though, and some of that tuning is just shifted to the tuning costs instead of tuning gains. I guess I didn't write that. You also can incorporate constraints on the inputs. That's a negative for both of those two things. And then finally, for optimization as control, well, it's nice. You can include constraints. You can have any cost you want that's convex. You can have linear dynamics. Directly solves this control problem, but you don't get a feedback controller. What you get is a sequence of states, of controls rather. And as we'll see the next time, that can be a big problem when you have things like some noise in the system and stuff like that. So I'll probably go through the optimization thing a little bit more next time again, but the next lecture we'll start talking about how do you apply optimization techniques when you actually do have some uncertainty in your system. How does that work? Because things don't always go as you plan. Okay, so we'll chat next time. All right, we'll get started. Let people filter in as we go. A couple things. The project write-ups are due today. I guess I didn't say in the email when they were, or the milestones rather. I didn't say when they were due, I guess. I said everything else is due at a certain time, but this can be due at midnight, it's fine. As long as it's in by tonight. And you can use late days on it too, but you might not want to. It's, doesn't ultimately count for that much because ultimately most of it counts. The final project is mainly just do you have enough to sort of that you've made progress towards getting there. A couple other things. Homework I can talk about a little bit as well. The last homework. I have some general comments on that. I think some people made similar mistakes, but do that at the end of class. Maybe if more people come in. So first of all, does anyone have questions about what we covered last time? I ask that every time, but I guess you probably would just ask if you had questions last time. Okay, so in that case, I'm going to start by rehashing a little bit what I talked about at the end of class last time, which was this controls optimization. And I want to spend just a little bit more time. I'll go through it maybe a little bit more detailed than I did last time. I had some MATLAB code last time that I didn't really describe at all, but I'll go over it in a little bit more detail now, and we can actually sort of see, taking this LQR problem and doing it in an optimization form. What are the advantages and disadvantages of that process? So here is our LQR problem, right? Here was LQR. We want to minimize over states and controls this sum from t equals 1 to our horizon h. The cost here, subject to the constraint that the states have to be governed by their dynamics, and that we start at some initial state x init. Now, unlike LQR, the big point here is that this is, so first of all, this is a quadratic program, right? It has linear constraints, linear quality constraints, quadratic objective. But unlike LQR, where what LQR gave us, remember, was a feedback policy which prescribed optimal actions as a function of the state, right? It said that ut is equal to some matrix k, and in the discrete time, or rather in the finite time, it's kt, though in the infinite horizon case, it's just a fixed k, times xt. And so if we want the actual sequence of states and controls, we just plug the first one in, get our optimal control, see what the next state is according to those dynamics, and repeat this process. What we get out of this problem, and this is nice, as we'll see in a second, because it gives you not only the states and controls, but it also gives you an actual, it gives you the actual policy itself, right? It gives you the way of converting from states to controls. And that's a very nice thing because we can, as we'll see in a second later today, in the case where there's some noise in the system, you can actually still apply this without having to redo everything, essentially. So that's nice. But what we get with optimization instead is just an actual sequence of states and controls, right? We get the resulting u star 1 to t and x star 1 to t. So that's the controls you execute and the resulting states. And these are of course equivalent for this fixed problem, but there's a trade-off here. We no longer get an actual feedback policy. We just get the sequence of states and controls. So the nice thing, though, is that we can, unlike an LQR, directly incorporate, in this case convex, but still some sort of constraint. We can directly incorporate constraints into the optimization problem itself. So if we have the constraint, say, that the controls, we don't have, we can't execute control arbitrarily. We can't turn on a heater in a room that's 10,000 watts. That probably would be a pretty big heater. 10,000 watts actually isn't that big, but it's getting kind of big. So instead of just sort of prescribing any sort of control based upon the state in a linear fashion, we can directly encode constraints on these things. And this solution you have here can be quite a bit different than, say, if you take this control and just clip them to the resulting, to your allowable bounds, for example. You can get very different policies if you incorporate the constraints into the estimation problem itself. And so this is a big advantage here, because now we can actually, there are lots of times when you have natural constraints on controls, right? A generator cannot typically produce negative power. It typically has a maximum power it can produce. We saw that in the optimal power flow, right? We typically had constraints on generation at any given node. And if you just execute LQR control, you're essentially admitting you have to throw those out. Or at least in the control process itself, when you find the controls, you have to kind of throw those out, ignore them. Whereas in optimization, you can just put them into the actual framework, and then you directly encode these in the problem. And even when you have things like constraints like this, it's still a convex problem. Right? This is still a quadratic program. And so you can just plug it into a solver like YAML, or a specialized solver if you want to solve it faster, and get a solution out. And so we can solve control tasks with constraints, which is very nice, because they do have constraints in practice. Here is some code that does it. And I want to spend a little time on this. If on the last assignment, the homework assignment that's out right now, there is one problem which it's actually an optional problem on the homework, but I would really encourage you to look at it because it really does tie together a lot of what we've done so far in the class. And this sort of stuff here will actually help you if you want to do that problem, because the way you sort of encode these things in YAML can make a big difference about how easy it is to represent these, to encode these control tasks. So what I'm doing here is X and U. So X here is, our states in this case are these, this is just the same control problem we've had the whole time. It's trying to regulate the power of regulate the power angles of these 5 generator systems tied together with these DC power flow laws, right? That's what we've been studying so far. N here is the number of generators, that's 5. And the state corresponds to the thetas themselves and then the omegas, right? So X here, X is theta and omega. Each of these are vectors in R5, so the whole thing is in R10. And U's are the mechanical power, but it's the only control input we have at each one, so we'll just call it U. Now, the way I'm writing this here is somewhat important because it can be trickier. And remember last time, we knew from last time that there's essentially, you can encode this with this state as xt plus 1 equals axt plus b ut plus little a, right? Where these are all properly defined in terms of their continuous time analogs, then we build in the integration time step into this thing. Okay, so I should also say the control with optimization is a lot easier to do in the discrete time sense than in the discrete time case than in the continuous time case. The LQR, there's sort of a closed form for it. You can actually do it in continuous time. Control here, optimization, it's hard to optimize over infinite dimensional things. I mean, you can kind of do it by like parameterizing controls and stuff like this, but it's a lot harder. We're only going to talk about controls optimization in the discrete time case. So we have our dynamical system here, and what's somewhat important here is how I am writing these variables in YAML. So I'm defining a matrix X. Probably you should use big X for that instead of little x, but big X here is a 2n, so that is 10, by T matrix. Where really what this is a matrix where each column here is one set of states. So x1 is the first column, x2 is the second column, all the way up to xt. And this is not the only way to do this, right? You could also make a really long single state vector that was something like this. That was, right, x could equal a vector in 10t where you have x1 first, then x2, these are all vectors themselves, then all the way down to xt. You could do this. In fact, you're going to have a setup like this on the second problem in the homework. But this is a little bit more cumbersome now to write, because what we want to write in this problem is we want to have this equation hold for all the different state control pairs. And I should say I'm doing the same thing for U. So I'll erase that. We don't use that formulation there. Doing the same thing for U. So U is a matrix in 5 by T. Okay? And we want this equation to hold for all the different state and control pairs here. And you could do this in a lot of ways, right? You could use a for loop for this. There's lots of things, right? You could use a for loop and then index into the right elements of that big vector you put together. That's completely equivalent. And in fact, the YAML will just do that internally the way we do it here. Usually solvers think of all the unknowns as being a single vector, like you saw in the standard form quadratic programming, but YAML sort of does all that for you. But here what's really nice is we have this one constraint right here that captures the first line of the constraints there, that captures the dynamics for all the different time steps. Right? So what we write here is, let's see, put it like here. We write here is we write x 2 to the n equals a times x 1 to the n. I'm going to cut off, I might cut off here, 1 to the n minus 1 plus b times u 1 to the n minus 1 plus a, where a is actually here also a matrix with this a repeated t different times. Okay, and what this is doing is it's saying these, this part here, this matrix here, equals a times this matrix here. Right? And that's actually completely equivalent to saying that this thing holds for all the different time steps. We're saying this sort of second submatrix here equals a times this first submatrix plus b times the first submatrix of u. First submatrix isn't done right. It's the first t or all the t to the t minus or 1 to the t minus 1 columns. And in general, when you can do things like this, when you can put formula like this in a matrix form instead of in with a for loop in vector form, your code will just be easier to debug. I mean, this is much more straightforward what's happening here, rather than if you try to look at the indices and iterate over the right indices. That could be pretty cumbersome, and this can be much easier to do. So, as a general note, you can play tricks like this to make MATLAB or YAML code at least look a lot nicer. And then we just solve the. Oh, I should also say we also have these constraints, right? So we also have the constraint that u, and that's all the u's, is actually managed to write it like this, the other way around. That u is greater than or equal to u star minus 0.5 and is less than or equal to u star plus 0.5. So all the u's have to be bounded within plus or minus 0.5 PUs over and above their nominal, under or over their nominal amount. Right? So again, this is just sort of encoding those constraints that this has to happen for all of them. And here u star is a matrix that just has all the constraints repeated for all the different generations for all different times. Okay, and then we just solve it with our normal thing. One thing here is I'm calling the norm x minus x star. That's just our objective, right? We're just doing we're taking Q essentially to be the identity matrix. And one thing you might not have seen before is there's this little term Frobenius. So in MATLAB, you have two matrices, or if you have a matrix and you want what you think of as the L2 norm of that matrix, you want all the elements of that matrix squared and summed up. That actually is called the Frobenius norm. The 2 norm for matrix means something a little bit different, which is not something we're going to deal with here. It's like really singular values of a matrix, which is sort of weird actually to me that MATLAB has this not be the default norm for a matrix. Because it's always what you want, and sometimes it makes MATLAB crash because you take the norm of a matrix that's too big to compute the other norm for it. Anyway, that's kind of a tangent there. So what we do is we just solve this problem. Here, essentially, we have The cost on the control is a third, well, 1 e to the negative 3 times this norm. So we want to be within a certain, we want to be close to the nominal control, but we have less of a penalty on that than we have a penalty on deviating too far from the desired states. And these are just essentially encoding those Q and R terms in our LQR cost function. So we run that, and it looks, I should also say, it takes, this is a pretty big problem, right? I think T here, well, it says T was 10,000 here. And there's 10 by 10,000, so there's 100,000, 150,000 variables that you're optimizing over here, which seems like a lot, right? You certainly have less variables than that in your homeworks that you did, and those will take a long time for Yama to solve sometimes. But what's nice here is that there's a huge amount of structure in these equations. So if you were to look at all these constraints, most of the constraints would actually be sparse. Essentially, there's no relationship between most of the pairs of variables. And because of this, Yama can really efficiently optimize this thing, or it knows how to efficiently formulate a solution that then the solvers know how to solve very quickly. So it's pretty impressive. You can solve something that big in about 10 seconds on a single desktop. This is without any optimization. I just plug this in and run. Again, though, that what you get out of it is a sequence of control actions, not a single feedback controller. So have to keep that in mind, right? We don't get something like this. We just get a whole set of views. OK, here's what it looks like. I think I showed this last time, so I won't dwell on it too much. But basically, what it's doing is that you remember the LQR controls that are executed, right? To get to the desired positions, LQR will execute sort of really, really big negative powers at first. What's happening at first is that some generators are behind where they need to be, and some are ahead of the power angle they want to be. And so it's really sort of putting the brakes. And what that really means is stopping and consuming power instead of generating power at some nodes, which is not really realistic, right? It's essentially saying that, I'm going to somehow start consuming a huge amount of power at a generator, which isn't really that easy to do. What happens here is that we're constrained to only generate 0.5 less or 0.5 more than the nominal power for each generator. And so you have a much smaller range. The y-axis on this scale was went from -8, and this one goes from -2 to 3. And you see that you do, in fact, hit the boundaries a lot of the times, right? You do, in fact, this generator is at its lower bound for a while. Then it goes up to its upper bound for a while, because all the other ones do the same thing here. And then they sort of settle, and eventually everything settles to their desired amount. And you can see from the top there that the desired thetas minus the true thetas minus the desired thetas do all converge to 0. So we are correctly tracking the desired state through this, even though we do not take actions that are beyond our prescribed range. So to summarize, and I had this slide up last time, but I'll say it all again. We've covered 3 different ways of doing control, or thinking about control in some sense. We started with PID control, which really was about this kind of intuition that, if you're off by some, we'll just apply control to kind of correct that. So it's very intuitive, but and easy to implement because of that. But the problem with PID control is it really can be tricky. It doesn't always apply, right? So if you have fewer controls than you have states, that can be hard to think about. Well, what if you didn't have control at one generator? Couldn't its power was essentially very limited or fixed. How do you get that generator to get to a better angle? You can, right? You have some control over this, right? Because the other generators are doing their own thing. Maybe you actually could get it to its desired power angle still, but that's kind of tough to think about how you do it. But actually, in this case, we know we can, because there's sort of one generator kind of has an arbitrary angle anyway, so we know we can do something like that. But it's hard to think about how PID control works then. If you need to steer not just your own self to a given state, but you want to steer other related states also to a desired state, it becomes much harder to think about what's the right control action there. So that's the problem with PID control, though it is, I should say, emphasize again, extremely widely used in practice, because it's very easy to implement and it's very intuitive. Then we talked about LQR, which was sort of the next step up. It was our first take into optimal control, or first step back into optimal control, I guess, where we now have a cost function we're trying to minimize, and we come up, we know the system, it's a linear system, we have a cost function, and we get out from that the best possible controller for minimizing that cost function. What's nice here is that we still have a feedback controller. It's still really easy to compute if you have the model, not that it's that easy to do algorithmically, but MATLAB has a command for it. It's one line in MATLAB. And it also is widely used, the LQR control. And now it also can, by the way, be applied. And we'll see this a little bit in a couple lectures from now. We actually can apply LQR very successfully to cases where there are more states than controls. So you actually, LQR will give you this really nice way of figuring out how to adjust your own control input to affect other states as well. That's really impressive. Problems, can't incorporate constraints. And it does require a model of the system. Right? You need to plug in that A and B terms into the LQR function in order to get a controller out. Unlike in PID control, where you just kind of set it up by intuition. So pluses and minuses there. And finally, we have this optimization control, which is very nice because now you can incorporate constraints into the system directly. It directly solves the problem we care about in some ways, right? You can constrain the state if you want, you can constrain the control if you want, and just directly solve the problem. The disadvantages are, though, is that, first of all, it actually can be still relatively time-consuming because you have to solve an optimization problem to get the control. And it does not give a feedback controller. And then we'll see what this is a problem, why this is a problem in a second. Just because, especially in the case where we have some noise in the system, if we wind up in a different state from what we planned, this can actually cause big problems. And we can sort of not know what to do. So with that said, let me jump to our, actually, first of all, as I always do, maybe not often enough, are there any questions about this whole paradigm here? Okay, then let me jump into the next unit, which is going to be talking about this case where we do have noise in the systems now. All right. All right, so I'll talk about this setting I introduced a while back, but just talking about the dynamics of the systems, where our system, rather than having a system where we know exactly how the state will evolve, we have xt plus 1 equals f xt ut. Rather than this, and this implies a lot of things, if we really have a model like this is pretty impressive, because it basically means that if we ever know the state, we can know exactly what will happen every time point in the future, given whatever control we want to do. This is a pretty sort of powerful model. We'd be able to, if we had this, we would have a pretty powerful model of the system. Instead, what people often do is look at systems where we don't quite know what's going to happen. So we have some noise term, which I'll call epsilon t, which adds some noise to the system, so we don't quite know what the next state's going to be. We just know where it'll be on average. And I think before, what we're going to cover in this lecture is sort of 3 different paradigms for stochastic systems. And these were on the first line I wrote at the end of class. They all had acronyms. They were LQG, MDPs, and MPC. So we'll see what all those mean, first of all. They stand for, the LQG stands for linear quadratic Gaussian, which is essentially the algorithm you apply to stochastic systems. It's the analog of LQR for stochastic systems. MDPs are Markov decision processes. Those we saw already, but now we'll talk about how to actually solve these things. And then MPC is model predictive control, which will be kind of one of the big paradigms we use for talking about control in the rest of this course. Okay, so as I wrote there, what happens to our systems when we don't quite know what's going to happen to them? There's some noise in our dynamics, and this noise can arise for a lot of reasons. There either can be actual real noise on some level, whatever that means, right? Because maybe it's at the molecular level there's no noise, but at the meta level there is noise. There could be real kind of noise in the system, though. We could really believe the system is uncertain. Or we could just have, for example, errors in modeling the system, right? If we don't quite have a great model, that can actually often be captured by noise. Maybe we actually have a simpler model than sort of the true system out there. And when you look at a simpler reduced dimension model, you do have a model that can't quite perfectly predict what's going to happen. This is sort of, this is a very common thing, right? For example, our predictions of the power consumption tomorrow based upon weather that we have with machine learning, those effectively had some noise in them, our predictions, or the truth was like our prediction plus some noise, right? Because we weren't getting an exact model of exactly how much power there's going to be. We were predicting kind of on average what it would be. And then if you want to sort of model what the real system does, you would say the real system is, our model maybe plus some noise term. That would be a reasonable way of modeling something like how much energy is going to be consumed tomorrow. So things like inaccurate predictions could certainly bring noise, effective noise in the system as far as we're concerned. And for our sakes, we're not really going to be concerned about differences between modeling error or real stochasticity or inaccurate predictions. They're all modeled for our purposes by this one noise term, epsilon. But now the question is, we based our entire optimal control paradigm on the fact that we want to minimize the sum of costs, right? We want to minimize the sum from t equals 1 to some big T. I guess I switch between using h and t there sometimes, but it should be obvious by whichever one I'm using, which one I mean. So we want to, in optimal control, we want to minimize this cost function, which we call j, which is the sum from t equals 1 to big T of these costs, right? The costs of xt and ut. But now, all of a sudden, we don't know what state we're going to be in anymore, right? Because there's noise in the system. Even if we know we're in state xt right now, we don't know what state we're going to be in time t plus 1 because there's some noise, right? We don't know this ahead of time. So what is this thing even, right? This thing isn't even really well defined because there isn't a true next state that we're in anymore. Now, of course, there's some obvious candidates for what you could do instead. The most obvious, maybe, would be taking the expected cost, right? So you just, rather than this, because there's noise here, and I'm saying this kind of informally I'm using expectations here somewhat informally, but don't worry about that. I think everyone sort of gets the basic idea of what I mean here. So we just take the expected value of this thing. That means on average, what's the cost going to be? If we average out over, say, many different runs in our stochastic model, what will the average cost be? And the nice thing about this is that really actually, almost, if you write it like this, there is a sum here, and so we can take the expectation inside the sum. This equals the sum from t equals 1 to t of the expected value of the cost at time t. Now, depending on the dynamics that link these things together, this could actually be complex, right? Because the dynamics, they're nonlinear, as we saw before. Those don't necessarily preserve expectations. And so you can have sort of very complicated actual forms of what this thing really is once you write the dynamics in here. But in terms of the actual cost itself, it's very nice. It just says what's the expected cost at the sum of the expected costs over all time. And in fact, this one is sort of so obvious that people usually just use this one without even saying it. They just assume, of course, you're going to minimize expected cost. That's what you do in a stochastic setting. But just to highlight this point, there are other alternatives we can do instead. Right? So another one we might want to do is, well, maybe we don't really care beyond a certain point what our cost is. We just want to make sure, so say, you know, what you can essentially do here is look at a distribution of costs, right? So you have some, this is, I'm not sure how to label this axis actually. I mean, this is just sort of this is your cost and this is the probability. I guess that's the simplest way of doing it. So you have some cost function, and you have some probability of having that. And it could look something like this, right? Where you have some distribution of costs here. And we might be in a situation where we don't really care what our cost is as long as it's below some threshold. So we're fine, we're sort of happy over here. And this is really bad over here, though. And a natural cost function in that case might be to say, we actually want to minimize the probability that our cost exceeds some threshold. Or the sum of the cost exceeds some threshold. Right, so that's this one here. J would be the probability that the sum of these costs exceeds some threshold C. So I guess this is why I was sort of nervous about this. This is sort of this is actually this J. This is this one without the expectation there. For a fixed set of disturbances here. And this is this probability. So it's a little confusing here if I'm writing J equals that probability. So maybe ignore this. Actually, what I should actually have done is written this. So this is the sum of our costs. Okay, that's better. And then J is whatever, expectation, maybe, or probability that sum of costs exceeds some threshold. So all these things are, and there are other ones you can do too, certainly. And in fact, you could, if you care about this, there are also other ways to encode this. Like maybe you change your cost function to actually be like a cost function that's infinite if you exceed that threshold and 0 otherwise or something like this, and that kind of then there's the value actually, or if you change it, have a different cost function where your cost function is 1 if you're over this and 0 if you're less than this, then actually the expected value of that new cost function would be this probability. So you can play tricks like this and kind of make these things similar or put these in similar forms here. But the only point I'm really making here, because we won't deal with this one at all, we'll just deal with expected cost for the rest of this course, really. I just want to make the point that there are other possible options that you can use. However, as I said, it's much more common to see expected cost being minimized because depending on how you define cost, you can get very expressive with that. And it typically is a lot easier to minimize things like expected costs rather than other costs you may come up with. Okay. That little comment I made about the new cost you can introduce makes sense. It's a little bit weird, right? So let me just sort of explain that because I'm worried about it being a little bit confusing otherwise. So what you could do instead is define some sort of new function C tilde, which is equal to 1 if the sum of the costs 1 to t C x t u t is greater than C and 0 otherwise. This is a function of all the states and controls now. So this is really a function of all of them. It does not decompose over the states. So this is a but it's still a cost function on states and controls. And the probability that this thing exceeds that is just equal to the expected value of this. Okay, that's all I was saying before. This cost function here, I mean, this isn't really a cost function, right? Because we define cost functions as being for a single state in control. It's just kind of almost a definitional thing where we're saying we're defining some new multi-state in control cost that really is just this thing. Okay. Tangent done. And as I said, we use the expectation because it's pretty easy, typically. It's easier because you have these things. You have this decomposition over the states there. Or over time, rather. All right, now the bad news, which we saw before a little bit, right, and when we just talked about stochastic systems, the bad news is that exact optimal control is typically a very hard problem. When you have a nonlinear dynamics and arbitrary cost functions, or even just arbitrary noise that isn't, of one of a couple forms, it can be really hard to optimize these things. That's somewhat expected, right? Because we talked about before, the expectations can get completely the expectations can go through with these cost functions, and they can no longer be linear. So you have all these cases where when you have dynamics and cost functions, those can really warp, and then also noise, it can really warp the expected states. And in the worst case, what you have to do is you have to keep a record of the probability of being in any state at every time, right? So what you really need to solve it in general is you need some distribution over your states at all time. And of course, the state is a n-dimensional vector, so you need some way of representing arbitrary probability distributions over an n-dimensional vector over all time, which is not really doable. Right? And so there are only a few cases where we really can solve these exactly. Those are important special cases. But the point being that we don't want to do this. We don't want to maintain a distribution over all possible states we could be in. That's the only way to do this kind of truly optimally in some cases. The good news, though, is that we can solve certain special cases. So as I was talking about before, things get very nice when things are linear, right? So if we have the case of a linear dynamical system with Gaussian noise, even if it's partially observable, then we actually still can control the system. And actually, I wrote LQG before as a thing, linear quadratic Gaussian, but really LQG is usually only, that's meant for the case where you also have partial observability in the system. If the system is fully observable and just stochastic, it's still called LQR. So just a little aside there. So we can handle the case of linear systems and Gaussian noise, even with partial observability. We can also handle the case of Markov decision processes. This one only when it's fully observed, not with partial observability. We can do that theoretically. I mean, there are such problems too, but they're a lot harder. And MDPs, remember, had this nice property that we were talking about a finite number of states for them. So unlike a real vector that has an infinite number of states, MDPs have a finite number of states. And those we can solve also in this full stochastic setting. And then finally, even though this is not an optimal approach, there's this technique which we're going to talk about a lot in this class called model predictive control, or MPC, that really works well in many cases, even though it's suboptimal. And this is an approach based on optimization that essentially is the extension of that optimization paradigm, control of optimization paradigm, to the stochastic case. And that essentially involves dealing with this fact that you plan some controls ahead, and what you actually get might not actually be what you planned for, right? Because there's noise in the system now. So we're going to deal with that in a way called MPC. So let's sort of step through these things one at a time. We're going to first talk about linear quadratic control with Gaussian noise, then MDPs, and then MPC, if we get to it today. Okay, so first of all, linear quadratic stochastic control. We have our system here, linear dynamical system, possibly with an affine term. Doesn't actually affect things because it just falls off. I'll just write it without the affine term. So epsilon t, where epsilon t here is a normal random variable with zero mean and covariance sigma. In this class, we don't really talk about too much what this really corresponds to. Don't really worry about this. If you know one-dimensional Gaussians, this is just sort of a matrix times a one-dimensional Gaussian to get a vector of Gaussian random variables. But this is just the Gaussian random variable that's vector valued. And our cost function we're going to consider is the expected sum of these quadratic costs. equals 1 to t of exactly what we had before, qxt squared plus r ut squared, but taking the expected value of all these things. Now what's really amazing here is that even though you have a noise term, and so this seems much more complicated than LQR, because now the system is stochastic. What's really amazing is that the exact same solution is optimal for this system. So remember, we had K, and actually I should say that this LQR here is really solving the infinite time horizon case, but the same is true for the finite time horizon. In general, you have the fact that the best action you could take at time t equals some matrix K times xt, whatever state you happen to be in, where this is time varying in the finite time horizon case, but constant in the infinite time horizon case. So you can do this with either this going up to h or going up to, I guess I wrote t there. I'll just be consistent with the slides. You can either write h here or infinity, either one works. But in both cases, your optimal control here is equal to just this thing. And even what's really kind of surprising is that to get this controller, I'm not actually talking about my noise anywhere. Even the distribution of it, right? This noise is characterized by this distribution, covariance sigma. And that distribution does not factor in at all to the optimal control law. So that's really surprising. And the reason why this works is that, well, first of all, what we saw before, right? So the states themselves are nice because they're all linear. So the expectation of this thing, you just take expectations through here because everything is linear. Use a quantity we choose. Expectation here is 0 because this is a 0 mean random variable, so you have relationships like this. And they hold as you progress in time. And so that's the first thing. The second thing, which is very cool, is that this particular cost function is kind of special in that the expected value of a cost like this, when xt is Gaussian, and it turns out that all the xt's, because of this form, all the xt's themselves end up having a Gaussian distribution. This thing here just equals this cost applied to the expected value of xt plus a constant. It's not exactly equal to this, but it's equal to that plus some constant. Where this constant here, yes, this constant will depend on the distribution of noise you have, but you can't really change, no matter what you do, you can't really change that. That's going to be the same no matter what you do. And so the best thing to do is to actually just sort of ignore this constant term and control this as well as you can. And that ends up being exactly just the LQR problem. Right? There's no, this is all an expectation. Everything is just linear here. There's no noise in expectation. You have this thing in expectation, so really everything is just is fine. You just treat it like an LQR problem, and the noise doesn't even come up in the derivation. I should also add actually one thing. In the infinite time horizon case, it is the case that technically this thing is infinite, right? Because this thing sums an infinite sum of additional constant terms like this. So what you do in the infinite case is you actually just divide by, you take this with a limit as t goes to infinity, or as h goes to infinity, of 1 over h times that thing. But that's just sort of a technical mathematical thing. In the finite time horizon case, you just add a constant term to the entire cost. Okay, so that's sort of a surprising but very nice fact that if we have a stochastic system that is linear with Gaussian noise, it doesn't matter. We can solve it as if there was no noise at all. And that one is still called LQR. I think I did misspeak a little bit earlier, saying that LQG referred to all of this. LQG refers to the case where you have a partially observable system. This is just still called LQR because the algorithm is exactly the same. There's no difference. All right, now there's the case. Oh, and I should, right, I'm going to plot it, of course. So actually, let's see what this looks like in our, and this is actually an important plot. So let's see what this actually looks like now when we want to control our generators, but where there is some noise in the dynamics so that our next state is not exactly equal to AX plus BU, but it's equal to AX plus BU time. The dynamics of the generator plus a little bit of noise. This could correspond, for example, to some random fluctuations around the desired power, around the load of the power, right? So remember that our system was something like C plus 1, XT plus 1, where X here was our same thing as before, theta and omega, AXT plus BUT plus AT. And in this term, there was a term that had the loads. It was something times that, but it was something times the loads in that A term. So one case where there would be noise in the system, for example, is if the loads themselves have a little bit of noise in them, which is very natural, right? Because we don't know at the generator level, we probably don't know exactly how many light bulbs are on at every given time. The load's not a fixed thing, but it's going to be changing a little bit. And we can assume that we have it right on average, so the expected value of this noise is 0, but we'll assume this is changing a little bit. And here's what it looks like. So here is a plot now of our, I'm going to not plot the evolution of omegas just because you can sort of figure out what omega is from looking at the thetas. Omega is just the time derivative of that. So when these are constant, omega is also kind of constant, and they changes accordingly to how theta is changing. But I'll just plot theta minus theta d here. How far we are away from our desired power angles. So we start off far away like we do in all other control tasks, and we start going. And what happens here is that unlike the previous case, we never actually reach all the generators having 0 error. And that makes perfect sense, right? Because we're going to have some error due to this thing. Even if we get to the exact desired state, next time it won't quite be there anymore because we'll be bumped off by that random noise term. Right? And so we're never, unlike the other case, we're never going to quite reach it, where we want to be. But we kind of get close. And honestly, that's probably good enough, right? We don't probably have to be exactly at some desired state. It's sort of arbitrary what we sort of pick anyway. So it's good enough to kind of get everyone close to there as long as they sort of stay there over time. They don't get too far away. And what you see also is that the control actions you take are correspondingly they don't converge to a single power like we did in the non-stochastic case. All the mechanical power would converge to the right amount that we specified. Here, because this load is varying, well, of course our generation is also going to be varying as well. Kind of to track that, right? So what happens is that the generators in themselves kind of go up and down a little bit to account for the noise in our system itself. Now, probably the most important take-home from all this is that we can do better at regulating this if we allow ourselves to take bigger control actions, right? So by changing, for example, the cost in our LQR problem, by lowering the cost on control, say, for example, we will, in effect, have a bigger K matrix. That means little deviations away from where we want to be take us still sort of, make us apply a bigger control input to get closer back to where we want to be, and you can get things like this. So this is now the same exact dynamical system, but just with a different set of costs in our LQR function. So now we're getting closer there. We're still not quite there. There's still some variation around where we want to be. But you see we're paying for it in how jittery our controls are. And this makes perfect sense, right? Because what happens is, that we get almost to our desired state, noise kicks us off a little bit. And our old controller would kind of say, okay, well, we'll apply kind of gentle control to get back there. This one's saying, no, we really want to get back there fast, so we're going to apply more control. And what's actually better here, neither one of these is sort of objectively better than the other. What really is better in practice is what's the actual cost of varying your control like this. This is probably a bad, I mean, certainly at this amount, this would be a horrible thing to do with real generators here. This is in seconds here. That would be crazy to do. I don't think they actually could even do it physically. Which also brings up another point about sort of the constraints you can't encode in LQR, right? Because in optimization, you could encode constraints that say your control cannot change too much between times. Here, we're just letting it change as much as we want. And so what's better, it kind of depends on your problem. Do you want to have fast control changes that get you right back to a very close around your state, or do you want to let that float a little bit at the benefit of not having these extreme swings in your control? Another nice thing, which sort of is almost, it's sort of actually very subtle here, is that it's sort of, what I'll say actually, well, I'll say this. We are not actually at any sort of set of states that LQR can predict here. So thinking this is an optimization problem, we're not actually at states that we would optimize to be at, right? Or in this case, the expected states that we think we're going to be at. The nice thing here is that because we have this feedback controller K, we select our actions as some matrix K times xt, or maybe a time-varying one, either way. We can just apply this. So even though we're at some new state that we didn't expect to be at next time, we still just apply this constant sort of feedback, and it works pretty well. It kind of keeps us at our desired state, even though we don't know ahead of time where we're going to be. This is similar to PID control, right? PID would also work in a similar way, where it doesn't really matter. You know, we don't know where we're going to be 100 time steps from now. That's actually OK. We're just going to take actions based on this controller, and it'll keep us around where we want to be. And we can get, as you saw here, sort of arbitrarily close to where we want to be if we're willing to pay a big cost for it. And a big cost on more control. All right, one extension which I hinted at before was this extension to the case of partially observable systems. So we have this now stochastic linear dynamical system. Epsilon t is normal. And we have it be partially observable. So yt, which is what we actually observe, is some linear function of xt plus some other noise term, qt, where this is normal mean 0 and covariance q. We talked about before sort of this setting, right, where this was just deterministic, and our observations themselves were the ones that were noisy. And we talked about this case too, I think, where we had some systems that we weren't necessarily controlling, but which just evolved noisily, then we got noisy observations from it. And now we're talking this sort of full case where we have everything in it. So we have controls, we have noise in the dynamics, and we have partially observable system with noise in our observations. And if you remember about the partially observable systems themselves, what I said, I guess this is sort of very, even more hand-wavy than LQR, because this is something we're not really going to talk about at all here. But there was a way to estimate these states as well as we can. And this was called the Kalman filter. So the Kalman filter, what it does is, given a sequence of states, it says what is the best estimate of our, sequence of observations, what is the best estimate of our current state? And it does that by essentially solving a least squares problem, a weighted least squares problem, effectively. Now, for this problem, this linear quadratic Gaussian problem. Linear dynamics, Gaussian noise, partial observability. Something pretty amazing happens. And what this is that the best thing you can do is to estimate your state based upon a Kalman filter, which completely ignores the fact that you can control the system. That's just using this thing here and the dynamics, but only in terms of what's happened before, not in terms of what you're going to do next. So you apply a Kalman filter to estimate what state you think you're in. Then you just apply the LQR control, and I'll call that x hat t is the estimated state. At time t. And what you do is you just apply the LQR control to this estimated state. Actually, that's even more than estimated. It's the expected state. So there's some, you'll actually get a distribution of our possible states using a Kalman filter, but you just take your expected state. And you apply the LQR control based on the expected state. This is something called the separation principle, meaning that you can separate out the filtering task from, that's the estimation task, from the control task. So again, this K matrix was constructed without any knowledge of the Kalman filter, sorry, yeah, it was constructed without any knowledge even of the noise terms at all. Those did not factor in at all to constructing this controller. You ignore them. Similarly, for the Kalman filter, that we won't go into it, that ignores entirely any sort of cost of the system, any notion of the fact that you can control the system. It ignores all that. Yet what's still not just good, but the best thing you possibly can do, provably optimal, is just run the Kalman filter and then apply LQR. And this is called the separation principle, and it's actually, this case is one of the few cases that this actually does apply. So this is the exception, not the rule. In a lot of situations, you can, a lot of stochastic systems, you can apply some filter to estimate where you currently are. And you could apply some control that, if you knew where you are, would be optimal. But the combination of these two things is not optimal. It can be actually arbitrarily bad. So this case is one of the cases where it actually this does hold, and it's kind of special for that reason. What we will see next when we talk about MDPs is the case where we can still solve optimal control in the stochastic setting, but if we have partial, and we can also separately estimate our, given a sequence of observations, estimate where we think we are, but it is no longer optimal to combine these two. And you have to sort of take into account partial observability when you're doing planning. And that we won't talk about at all, but just know that it's not the same thing. The separation principle does not hold, for example, for Markov's decision processes. Okay, so I think that actually finishes up our stuff on LQG here. Is there any questions on this? Have to be some, right? This is starting to get a lot of information thrown at you, I know. Yeah?
Verify that it doesn't matter whether the noise is correlated?
Correlated in what sense? So typically what you have is the noise is independent over time, so it's not correlated in time. You actually can make it correlated in time too, and have this thing does still work. It's a little bit trickier. But the noise, different noise terms here are correlated. So the correlations in a Gaussian random variable are specified by the covariance of that variable. Again, if you haven't seen this, don't worry. We're not going. This is not sort of a core part of the material here. But the covariance in a Gaussian determines how correlated the individual components of this noise are, and those certainly can be correlated. I mean, that's completely fine. And you actually can have correlation in between time too. That's actually also fine, as long as it's all Gaussian. But that's less common. That's not in the model here, I will say. I'm not writing that here. Anything else? Okay, so let's take a brief detour then and talk about MDPs. As I said, MDPs are not what we mainly focus on in this course because most of the control problems we see in things like the smart grid actually have continuous states. There's just an actual power angle to a generator. It isn't like you can discretize that into one of a couple bins. I mean, I guess you could do that, but it's not that natural to do. But some problems either really can't be solved with these other techniques, so you have to discretize them to have any chance of solving them, or they're sort of naturally discrete. Now, I mean, a lot of sort of control or planning tasks there's one of two things you can do, and you can be in one of n situations. So there are definitely domains where the MDP formalism fits much more naturally. Here we'll just talk about it enough to get the basic ideas, but it's not a big focus here, so if this moves a little bit fast, you haven't seen it before, don't worry too much. All right, so remember, an MDP is a setting where we have a state xt, but this, rather than being a vector, is now just belongs to a set, a finite thing. So I'm saying n is the number of states here, but it's important to know that n is, this is either 1 to n. It is a single number what the state is, 1 to n, and it's a discrete number, and the control is 1 to m. So I'm using the same n and m sizes here, but it's important to note that this is talking about discrete. So a one-dimensional continuous state is bigger than this for any n. Has really more possible states you can be in. And same with control. We also have transition probabilities. And what these encode are is what's the probability that my next state equals j, given my current state being equal to I, and also the next state equals k, and my control being equal to j. Actually, I use addition here. I use j here and then k for this. Okay, and that's encoded as a bunch of these just matrices, which we refer to as p superscript k ij. So essentially, each pk is a matrix that is n by n. That they have to specify for every next state and every current state, and a fixed control, because that's what we're indexing over. So for any current state, what's the probability that I'm in any given next state? So there's n squared numbers you need to describe that. Though of course they have some constraints, right? They're all positive. Their probabilities here, they have to sum to 1. I guess in this case, for any given I, the sum over all j has to sum to 1, right? So the rows in this matrix sum to 1. And then finally, there's also a cost function, which is really just an arbitrary mapping from this to r. And so this is really just, you could think of it as effectively an n by m matrix, right? Because it's just for every state and every control, just specify what the cost is. Because that's the setting. And now the way you solve this is with an algorithm that's actually very similar to LQR. Uses dynamic programming in the same kind of way as LQR does. But the idea is you build up what's called a cost-to-go function, or a value function. All right, and the value function j, okay, so I'll write it a few ways. So I'm going to write it like this. J star at some time tau is equal to the minimum over all u. So and I should write it like this actually. For a state xt is equal to the minimum over all the future controls. So control tau plus 1, all the way up to control t, of the expected sum of costs. t equals tau big T, the cost of xt ut, where this expectation here is really capturing the fact that the state dynamics have to evolve according to those transition probabilities. Okay? So what I'm going to do is I'm going to, and I'm writing the star here because this is the optimal cost to go function. So if I do the best thing I can do from now on, what's my cost going to be? And the idea of this algorithm for solving an MDP, which is called value iteration, is that you build these things up iteratively. So first of all, we know that J star t, that's the final horizon of xt, is just going to be equal to the minimum over u of c, xt, and u. Right? Because there's no more states after that. So you just have the one. You take one control. So this is the minimum here. Remember, there's a finite number of controls. So to find the minimum, we just pick the minimum. That's all we do. Right? And this ends up giving you, really think of this as a vector in Rn. You just take this cost, you minimize, you find the minimum value for each state, you find the best control you can take, and then you just look at that cost. It's a little bit weird because the control here, you never get to a next state at the final times. The control here is sort of meaningless. You just pick whatever control looks best right now. Turn off the heater, say, if your objective is not to waste energy or something like that. That's just for the final time. And then the next thing you do is you actually iterate over all. You iterate, from time t. Basically, we first have this, and then we're going to build j of t minus 1, j star t minus 1 of x, and then j star of t minus 2 of x, all the way down to j star 1 of xt. X, I guess I should just write like this, x1. X. I'll just write it as x because we already have the time there. So we're going to first compute this, which is easy. Then we compute this, then we compute this, etc. down to this one. And the way we compute this is that, well, we know the best, we know the cost to go for being in any future state. So we just say, well, j of t, I'm using t minus 1 here, j star t minus 1 of x, is going to be equal to the minimum over u. First of all, just this same thing, c xt is x u. But now we also have to take into account the costs of the next states. So it's equal to the minimum over u of this state plus the sum over all x prime. And really what this is saying is x prime goes from 0 to n. Or if you want to write it a different way, the sum of from j equals 1 to n. What's the probability that xt plus 1 equals j, given that we are currently in state x and we execute control u? So that's the probability that we're end up in state j next, times the value function of, I guess, j. Let me write it a different way, actually. Let me just write it as I have it on the board, which is just this probability of overall sum over all x prime, which is the sum over all next states. But it's important that x prime itself is really saying that we're in state. When x prime equals j, that means we're in state j. So sum over x prime, probability that we end up in state x prime, given that we're in state x, and then execute control u, times the value of t, jt, so one more than this guy here, of being in state x prime. Would have just kept writing there, but I just didn't want to get hidden by the projector too much. Okay, so this is saying essentially our optimal cost to go is we look at for every state, is we look at the best control from that state, meaning that we find a control that minimizes the sum of the current cost plus the expected value of the next cost, given that control. In fact, not the expected value of the next cost, the expected value of all future costs, given that control. right? And this iteratively builds exactly this thing. Because this one here takes into account the best thing to do from time t onward. And then given that, this here takes into account what to do at time t minus 1 onward. And the important thing is that each of these themselves, think of these, each of these is really a vector in Rn. So this is really itself, it's a vector in Rn. You just keep around a list of exactly what the value is for all the different states. And so this is why, for example, you need discrete states and discrete controls. In order to compute these things exactly, say to minimize over this, well, this can be a hard minimization problem if these are arbitrary functions. But if we had a discrete number of controls, then we know we can minimize over it, right? We just evaluate them all and pick the best one. So this minimization is possible. Similarly, representing a value function can be very hard in general, right? We need sort of to represent a value for every single state. The nice thing about discrete states is that we know how to do that. We just keep a number around for every state, and that's fine. So the advantage of having discrete states here is that we can represent the value function and just as a table. And these minimizations here we can do because we just check all the possible actions. We don't have to worry about sort of some continuous minimization here. We just find, check action 1, check action 2, action 3, up to m. And we're good. So that's the basic idea of an MDP. And the optimal policy then, by the way, the actual thing you should do if you're in state xt is you just find whatever action actually minimizes that. That's sort of obvious, right? The actual action you take is whatever action minimizes this thing. Okay, so that's sort of very brief there, but at least highlights some of the possibilities of an MDP. And if you want to learn more, there's lots of classes you can take on, probably there's classes on MDPs, but certainly classes on like AI or reinforcement learning or machine learning will cover some reinforcement learning, which will cover some MDP stuff. So there are lots of other classes that cover this in more detail. Okay, are there any questions about this? Okay, so in that case, we'll stop the lecture for today because I want to talk a little bit about the homework, but we can do that just informally.